Hello everyone. My name is Malik Arslan Sar, and I am a tutor for this course, Principles of Vibration Control. And this is the third live session of this course. And today also we will be solving some sample problems which are related to the content that has been taught to you in the week 3. And these sample problems have been inspired from the previous year assignments. So I hope these would be useful for you in solving the weekly assignment that has been given to you. So um, I think I'll get started, and meanwhile the learners can join as well. Okay, so my screen is visible. Okay, so maybe we can wait a couple more minutes because the time to start is exactly at 4. So we can wait for 2-3 more minutes, and then we can get started. Okay, so we can get started. So the first question is on screen, as you can see. Okay. Can you turn off your microphone? There is a lot of noise. Okay, thank you. Okay. So the first question we have is that the power spectral density of an excitation shows the presence of several peaks, starting with a base frequency f0 and subsequently the peaks at 2f0, 3f0 to infinity. So, what can be said about the nature of the excitation? Okay. So we know that the power spectral density measures how power of a signal is distributed across different frequencies. And so let's come to the options. In case of harmonic, we know that it has a single frequency sinusoidal excitation, right? Say of the form of A sine omega t or something like that. So there is only one frequency, so that is not the option here. Now after that we have the second option is periodic, and we know that in case of any periodic signal we can use the Fourier transform to break down any periodic function into a fundamental frequency and then its further harmonics which have peaks like 2f0, 3f0 if the fundamental frequency is f0. So we can say here that the second option is the correct option. After that, the other two options are the broadband excitation and impact excitation. So in case of broadband excitation, we have basically a continuous spread of energy across different frequencies, not the peaks. So here we are talking about peak frequencies at f0 to f0. Obviously that is also not the correct option. And in case of impact excitation, basically we have a force for a very short duration, and okay, someone is in the meeting. What happened? Okay, let me turn list. Okay. Okay. So yeah, the impact excitation is also very short. We have a very short duration of force in a wide range of frequencies, and we do not have discrete peaks in that case. So on the second option is the only correct option here. Now moving to question number 2, we have been given that a tuned mass damper is to be designed. So you must have studied the design and modeling of the tuned mass damper and some other kind of basically vibration isolators or dynamic vibration absorbers during the week. We have earlier also studied about the tuned mass damper. So the question here is that a tuned mass damper is to be designed for a primary system with stiffness 50 Newton per meter and mass 10 kg. The spring attached with the tuned mass has stiffness of 1936 Newton per meter. So what should be the mass of the secondary system for harmonic excitation at 7 Hz to achieve perfectly tuned condition? So we know that in case of these vibration absorbers, we have a primary system, say with mass m1 and spring, say k1, or you can denote it in any form. You can write it as kpp primary, mp mass, primary mass. So in a tuned mass damper, we have a secondary spring. Okay, let me denote it as k2, and a secondary mass m2. So what we are being given here is that the value of this mass m1 is given to us as 10 kg, and this primary stiffness has been given as 50 Newton per meter, and the stiffness of the secondary mass has also been given to us, which is as 1936 Newton per meter. Now we need to find the value of mass m2 for the harmonic excitation. So basically the external excitation force is given to us, and for that, let's say it's something f equal to j omega t, and the omega excitation frequency is given as 7 hertz. So basically it is in hertz, so we need to convert it to radian per second. So we can simply write it as 2 pi into f, which is 7 hertz. So it can be written as 14 pi. Okay. Now we know that in case of perfect tuning, the excitation, basically the excitation frequency for the system should match the natural frequency of the absorber, so that the perfect tuned condition is achieved. And okay, there is someone else is joining the meeting. Okay. So for perfectly tuned condition, we know that the natural frequency must be equal to this excitation frequency omega. So our natural frequency of the absorber will be under root of k2 by m2, which should be equal to this 14 pi. Now we need to find the mass, so we can write it as k2 upon m2 equals to 14 pi square. So from this value, from this relation, can you quickly give me the value of mass? Please simplify this and put your answers in the chat box. Okay, so you can write it as 1936 upon 14 pi squared is equal to m2, which implies m2 is equal to 1936 upon, let me simplify this using your calculator. I have not simplified it. So it should be 43.98 squared. Okay. So this is 1936 upon, okay, the answer is coming out to be 1. It should be 1934.7, which can be approximately said to be as 1. So yeah, so if the fourth option is the correct option in this case. Okay. Now moving to the next question. Consider a typical under-damped single degree of freedom system. Initially only a spring damper in parallel. Now an additional damper is further added in parallel such that the system still remains underdamped. Which one of the following statements is always true? Okay. So the question here we have is that we have a single degree of freedom system with a spring and a damper, something like this, M, K, C. Okay. And it has been given that the system is underdamped, so basically our zeta is less than 1. Now we are making a change where we are adding another damper in parallel. Okay, let me draw it here. Okay, so what we are doing here is that we are adding another damper, let's call it a C dash, such that the system is still underdamped. Okay, so now adding a damper basically is like increasing the damping ratio. Okay, so we are increasing the damping ratio, but we are not increasing it that much. We are increasing it such that the damping ratio is still less than 1 only. Now which one of the following statements is always true? Okay, so it has been asked that which of the following statements is true. Now we know that here, okay, so the options are given that when frequency ratio is less than root 2, transmissibility will increase with rise in damping ratio. When frequency ratio is greater than 2, root 2, transmissibility will decrease with rise in damping ratio. And the time period of free oscillations will increase, the time period of free oscillation will decrease. Okay, so basically the question is typically asking us about the transmissibility and the time period of the system. So let's focus on each individually. So we know that for transmissibility, I'm not going through the whole derivation, that you can do yourself also, and that has been done in lectures also, that you are giving a force of a harmonic nature, or for example f equal to e j omega t, then the response accordingly is x e to the power j omega t. Then you simplify, then you write the governing equation of the system, you simplify it, and ultimately you express the amplitude in terms of f naught upon k and upon something upon the denominator, in which includes the terms of stiffness and mass and damping of the system, which you simplify further in case of in terms of basically frequency ratio, etc. So the whole derivation I am not doing, I'll just write the final formula which we get out of that. We know that it comes out to be that transmissibility equals 1 plus 2 zeta omega square, okay, where zeta represents the damping ratio and omega represents the frequency ratio, upon under root of 1 minus omega square whole square plus 2 zeta omega square. Okay, so here this frequency ratio, we have to see what happens when this is less than 2 and when this ratio is greater than 2. Okay, so we know that when omega is equal to root 2, if you put it in here, it will come out to be that transmissibility is equal to 1. So when omega, or the frequency ratio comes out to be root 2, the transmissibility does not depend on the damping ratio, because this expression here you can see this basically this term will become equal to 1, and then the numerator will be 1 plus 2 zeta omega square, and similarly the denominator will also be equal to 1 plus 2 zeta omega square. So this would come out to be equal to 1. So in that case it does not depend on the damping ratio at all. Now what it is saying is that when the frequency ratio is slightly less than root 2, okay, so when this frequency ratio is less than root 2 and you put it in here, okay, I'll leave it as a task for you, you will see that the relation between the transmissibility and zeta will decrease with increase in the damping ratio. Okay, so the option 1 is not correct. Similarly, when this omega you put it as root 2, you can see that the frequency ratio when it is greater than root 2, the transmissibility necessarily does not decrease with the rise in damping ratio. So basically from this expression alone you can get it. So the first two options are not correct here. Now coming to the option 3 and 4, that the time period of free oscillation, whether it will increase or decrease. So we know that in case of damped natural frequency of the underdamped system, we have the damped natural frequency as omega into under root of 1 minus zeta square. Okay, so this is known as damped natural frequency of the underdamped system. Now what will be the time period? We know time period is nothing but 2 pi upon the damped natural frequency of the system. Okay, because there is some damping there, so the time period will depend on the damped natural frequency. That's why we are writing 2 pi upon omega d. Now, okay, so here you can see which one of the, okay, so now here we are in the question, it is given that we are decreasing damping. Okay, so when we decrease this damping here, okay, when we are decreasing damping, this overall term will increase, right? Because it's 1 minus zeta square, we are decreasing it slightly, it will slightly increase, and as the denominator increases, the time period should decrease, right? So the time period of oscillation should essentially decrease here. So that is the third option. So this option will be true. The fourth option is obviously incorrect because sorry, the third option is obviously then incorrect. So this will be our correct option. I'm sorry. I have been a little under the weather, that's why I had postponed the session on Saturday. Okay. So coming to the fourth question, the mass of a proof mass actuator is 1 kg. It can produce a displacement amplitude of 1 centimeter. Okay. The force in Newton it can deliver in the frequency domain is given by. Okay. So proof mass actuator is also another type of vibration absorber, you can say. Okay, and in case of the proof mass damper, you know that the the proof mass generates a reaction force to control the vibrations by basically accelerating its own mass. Okay, so here let's say that the mass of the proof mass damper is m, which is equal to 1 kg. Okay, so now we know that the force which it generates will be equal to mx double dot. Now you can see that the options are given in the Laplace domain. So basically, the frequency domain. So we will take a Laplace of this thing. So here again we can write it as, we can take the Laplace and we can write it as Fs is equal to m into s square, s square x of s. There will be some terms, additional terms f of 0 and everything, but initial conditions we are taking as 0 only. So we will neglect those terms. So our frequency comes out to be ms square x of s. Now we are given the displacement amplitude, which is 1 centimeter, and mass is 1. So we'll put 1 s square, and the displacement amplitude is 0.01 meter. Okay, it can be written as s square upon 100. Okay, so yeah, I think option 2 should be the correct option. Okay. I hope this is clear. This was very straightforward question, just formula based. Okay, now moving to the next question. A Hodel damper is basically a tune mass damper, a Stockbridge damper, an auxiliary mass damper, both a Stockbridge damper and an auxiliary mass damper. So would anyone like to tell me what is a Hodel damper? Anyone? So basically this damper, it is a purely torsional viscous damper. Okay, so it contains basically a flywheel, a free flywheel or inertia ring, which is housed in a casing which contains the viscous fluid, like we have studied about the viscous dampers as well. And in case of this damper, we have studied that so we have studied that these DAVs are of many types. Okay, we can connect the secondary mass to the primary mass by either a spring or by a damper, or by both a spring and damper. Now we know that when we connect it with the spring, it is known as an auxiliary mass damper. When we connect it with the damper, it is known as a tune mass damper. And when both spring and damper are used, it's known as an it's known as a dynamic vibration absorber. Okay, and here you can see that in this damper there is no spring. Okay, so since there is no spring, it does not fall into the category of tune mass damper, because we know that in tune mass damper or vibration neutralizer we have a spring which connects the secondary mass to the primary mass. In case of a Stockbridge damper as well, we have a spring there, so it's not that. Now the third one is an auxiliary mass damper. So it is basically an auxiliary mass damper. Okay, because there is only a damper. Both a Stockbridge damper and an auxiliary mass damper, no, it's not possible, because it is an auxiliary mass damper, but in case of Stockbridge damper we have a spring as well. So option 3 is the only correct option here. Okay, coming to question number 6, we have a single degree of freedom spring mass system is subjected to a sinusoidal force of 10 Newton amplitude and frequency omega along the axis of the spring. Okay, so we have a single degree of freedom spring mass system. Okay, we have a spring, we have a mass, and we have a sinusoidal free force equal to 10, let me write it as 10 e to the power j omega t. Okay, right? The spring stiffness is 150 Newton per meter. Okay, this is given. And the undamped natural frequency, okay, so the undamped natural frequency is given as 10 omega. And what else has been given? We have been given a damping ratio equal to 0.2. Okay, at steady state the amplitude of vibration is approximately, okay, so you can see that this is basically a question of you can say transmissibility or magnification, because we have been given the excitation force amplitude, and we are being asked about the wait, someone is in a meeting. Okay, so yeah, we are being given uh, the excitation force amplitude, and we have been asked the that at steady state what is the amplitude of the vibration, basically the displacement. Okay, so first of all we have been given that our omega n is equal to 10 omega. Now from here we can find our frequency ratio, which is equal to excitation frequency upon the natural frequency, and the excitation frequency is mentioned, it is as omega, so it will be omega upon 10 omega, which is equal to 0.1, sorry, not 0.01, so it will be equal to 0.1. Now in case of the static deflection in undamped natural frequency, we know that we can write x naught equal to f naught upon k, where f naught is the amplitude of the force. Okay, so you can very easily arrive at this also, as we have been doing in the previous lectures, that we are assuming x equal to capital X sine omega t or capital X e to the power j omega t. Then we are writing the equation of motion, and then the e to the power j omega t cancels on each side. Then we can express f naught in terms of this. Okay, it is very simple. So here also similarly x naught is equal to, now f naught has been given to us as 10 Newton. Okay, so the amplitude of the force, sinusoidal force, upon k, which is given as 150 Newton per meter. Okay, so it is coming out to be 10 upon 10 upon 150. Okay, so it is coming out to be 0.066 and so on. Okay, let me write it as 0.0667 meter. Okay, so this is basically my x naught. Now what we need here is that okay, we have been given the damping ratio so we can simply find the x or the steady state amplitude by relating this static deflection and the frequency ratio. Okay, so we know that the dynamic magnification factor, okay, which is what? The output upon the input amplitude. It can be written as 1 upon under root of 1 minus omega square whole square plus 2 zeta omega square, right? Now everything here is given to us. X naught we have just figured out, omega we have figured out, zeta is already given as 0.2. Can you simplify this, solve this, and tell me what you are getting the value of x? 0.0673. Okay, so you are getting 0.0673. So the closest option to this is 0.07. Okay, mine option is coming out to be a little different, but that is almost same only. 0.07 is the correct answer. Okay, so now question number 7 is a theoretical question. So, for an aircraft structure with repeated support in form of stiffeners, which one of the following statements is incorrect? Okay, so in case of aircrafts, we are using basically structures known as stiffeners in order to control the vibrations. So the first option is there exist two different bands of modes in vibration. The torsional modal frequencies are higher than the bending modal frequencies. Z stiffeners are used for vibration control. Z cross section has low torsional stiffness and high bending stiffness. Okay, so first of all, let's start with this option 3. So Z stiffeners, we know that we use them, okay, for vibration control only. So basically they are of this sort, okay, they are in the form of Z shape, okay, there are I stiffeners which are in the form of I shape. So they are known as Z stiffeners. Now these Z stiffeners are used for vibration control, this is true. Now the Z cross section has low torsional stiffness and high bending stiffness. Okay, so it is a very known fact. Why? Because we know that here in case of Z I cross sections or I cross sections, our this neutral axis or neutral plane, okay, the basically the mass or inertia is away, the majority of material is away from the neutral plane. So because of this neutral plane, the torsional stiffness will be basically low and the bending stiffness will be high. So this option is also correct. Okay, so these two are correct. Now since the torsional stiffness is low, the torsional modal frequency should also be low, and the bending stiffness is high, so the bending modal frequency should also be high. Okay, so low torsional stiffness implies low torsional frequency and vice versa. But looking at the option 2, it is just written the opposite. It is written that the torsional modal frequency are higher than the bending modal frequencies, which is incorrect. It should be the other way around. So this option is false. Now it's simple. There exist two different bands of modes in vibration, which is correct because there are two different bands. One is the torsional and one is the bending. So it can be either controlled by there are two modes, which are, one is bending dominated, one is the torsion dominated. As both bending and torsion can happen in the aircraft stiffness structure. So this is also true. So the only incorrect option here is option 2. So that should be our answer for question number 7. Now moving to the next question. Okay, so a precision instrument package, so basically it is a sort of a vibration isolator which we are using, needs to be mounted on a surface vibrating at 60 hertz. So we have a surface which can be known as our system, which is vibrating at 60 hertz. Okay, so our frequency is 60 hertz. And the precision instrument needs to be mounted on it. It is desired that only 5% of the base surface vibration amplitude needs to be transmitted to the instrument. Okay, so basically what it is talking about here is that our transmissibility ratio should be basically 5%. Our transmission should only be 5%. Assume that the isolation is designed with its natural frequency significantly less than 60 hertz, so that the effect of damping may be ignored. Okay, so we are using that the damping here needs to be ignored. Okay, the stiffness of the required mounting pad is close to, and we need to find out the stiffness of the mounting pad basically, which we are using for isolating the vibration. And now the key here is that this transmissibility ratio is given to us, which is given as 0.05, and we know that it can be written as transmissibility can be written as under root of 1 plus 2 zeta omega square upon under root of 1 minus omega square whole square plus 2 zeta omega square. Right, now here this thing is important, that the effect of damping needs to be ignored, so we will just ignore these terms. So our transmissibility ratio will come out to be 1 upon omega square minus 1. Okay, we will cancel this out. Basically it's inside square, so it will come out to be positive only. So either way, if it's 1 minus omega square or omega square minus 1, you will have to take the modulus, whatever the term is coming out to be. So omega here, okay, we need to get the omega from this itself. So we can take the reciprocal. It means omega square minus 1 is coming out to be 20, reciprocal of 0.05. So omega square is equal to 21. Omega equals root 21, which is equal to, wait a minute, root of 21, it is coming out to be 4.58257. So I can write it as 4.583. Okay, so this is our omega. Now since we need to find the stiffness, we know that omega is nothing but excitation frequency upon the natural frequency, which implies 4.583 is equal to, the excitation frequency is 2 pi into 60 upon the natural frequency is under root of k by m. So m here is given as 1 kg, so I'll just put it as 1. So it will imply that 4.583 is equal to 2 pi 60, okay, upon under root of k, and k is equal to 2 pi 60 upon 4.583 whole square. Can you find the value of this? Okay, so it is coming approximately equal to 6759.616. Okay, 6759. Okay, so the closest option to the answer we got is 6700 Newton per meter. So that is the correct option. Okay, is this clear? Okay. Now moving to the next question. Recall the typical transmissibility ratio versus frequency ratio plot for a single degree of freedom system under harmonic excitation. Okay, so the graph has been explained in detail in the lectures. So now the question is asking, what is the maximum stiffness of an undamped isolator to provide 81% vibration isolation for 200 kg fan operating at 1000 rpm. So essentially 200 kg fan here means it's our primary system. Our rpm is given, so we can get the omega out of it, basically the excitation the excitation frequency that we can figure out here. So basically the parameters of our primary system are given. Now for an undamped isolator to provide 81% vibration isolation, okay. So So 81% vibration isolation here means that 81% should be stopped, only 19% can transmit. So basically 81% vibration isolation means 19% transmission or transmissibility. So essentially we are given the transmissibility here. Okay, and we have to figure out the stiffness. Okay, so it is very simple in that sense that transmissibility is given as 0.19, and it is mentioned that it's undamped, so the damping factor is of the formula. So transmissibility can be simply written as 1 upon under root of omega square minus 1, which is 0.19 is equal to 1 upon omega square 1. So you can write it as omega square minus 1 is equal to 1 upon 0.19. Omega square is equal to 1 upon 0.19 plus 1. Okay. Let me do this quickly. Okay, so it is omega square is equal to 5.263 plus 1. So omega is equal to under root of 6.263, which is coming out to be 2.503. Okay, so this is our omega. Now from here we can easily find the natural frequency. Why? Because we know that omega is equal to excitation frequency upon natural frequency, and our excitation frequency is given as 1000 rpm. So we can simply write it as 1000 into 2 pi upon 60, right? Basic conversion. And omega natural here. Okay, omega natural we have to find, so just let me put it this way. We can write here omega natural is equal to omega upon omega, so it will be 1000 into 2 pi upon 60, right? Whole divided by 2.503. Okay, so let me simplify this. Okay, so omega natural is coming out to be 41.84, and the units are as usual radian per second, because we are putting everything in SI units. Now we need to find the stiffness. So we know that omega n is equal to under root of k upon m. So here k is equal to omega n square into m, right? And the mass of the system is given as 200 kg, and omega n we have just figured out 41.84 whole square. Okay, so when we multiply, this is coming out to be 350.00 Newton per meter. Okay, now you can convert to the options are given as mega Newton. So you can simply convert it by multiplying 10 to the power minus 6. So it will become 0.35 mega Newton per meter. Okay, so this is our required stiffness. Okay, so the wording of the question might be little tricky, but if you see it is asking for very simple things, and even the formulas are very simple. You just have to understand the language of the question properly, that what it is asking, what is given to us, and what the solution, what the answer is expected from us. So now let us move to the final question of today's session, then we can wind up. In a dynamic vibration absorber, the primary mass and stiffness are given. Okay, so the primary mass is given to us, and the primary stiffness is also given to us. Okay, now what has been asked? The secondary mass and stiffness. Okay, the secondary mass and stiffness are also given to us. The secondary mass is 5 kg and the secondary stiffness is given as 10 Newton per meter. The magnitude of locked frequency. Okay, so we have to find the magnitude of locked frequency. We know that the locked frequency or locked natural frequency of the system is when the absorber is rigidly attached to the primary system. Basically, this secondary system and the primary system are rigidly attached to each other. Okay, that time the natural frequency is known as the locked frequency. Okay, for that k we can simply find the k equivalent and m equivalent. Okay, the k equivalent in that case is equal to k1 plus k2, which is 3000 plus 10, which is equal to 3010 Newton meter, and the equivalent mass will be equal to m1 plus m2, which is equal to 25 plus 5 kg, which is equal to 30 kg. Now the locked natural frequency can be found as k equivalent upon m equivalent, which is 3010 upon 30. So this is coming out to be under root of 100.334. Okay, so it is coming out to be approximately equal to 10.016, or we can simply write it as 10. Okay, so the magnitude of lock frequency should be equal to 10. I hope this is clear as well. Now that is all from my side. If you have any doubts, suggestions, feedback, you can let me know. Otherwise, we can end the today's session for everyone. I will be uploading these slides to the folder which you already have, and the YouTube link of this video will also be posted soon. Do you have anything else to say, or should I end today's session? Okay, so I'll end today's session for everyone. Thank you for attending. Have a good day.